Hello, Zero B. Welcome to another week of Algebra 3. Um, this week we got testing. Next week we got testing. There's work keys testing next week. There's all kinds of stuff going on. Atlas testing this week and next week. So we don't have class today. And I thought, okay, all this matrix stuff is pretty good because it has it there on Khan Academy. It has a lot of videos that explain all that. So we could just do that. I said we could just come to class on Thursday. And I went, nah, with all the Khan Academy stuff, we don't need to do that. So what I did is I went and I dug up last year's video that covers the exact same thing. It has the Khan Academy videos, has me describing the assignment, telling you what to do this week. I said, I'll just pull that out of the archives and let you guys watch that. So that way you don't have to come on Thursday, unless, of course, your grade's below 70%. Or if you have questions, I'm happy to help you then. But this week, just watch this video from past me. I was a year younger and better looking back then. But anyway, here it is. Anyways, welcome. All right, let's turn on cameras, people. Let's make sure there's actually students here behind these icons. Let's say howdy this morning. Hope your Easter weekend was fabulous. We had a big meal. Had kids over, played games. Yeah, had a good weekend. Went and saw Ghostbusters Friday. That was good. Just a good movie. But it's great to see everybody here this morning. We've got a lot to cover today, but I've actually trimmed it down. I've decided we're not going to cover some of this matrices stuff just in the interest of time because, you know what, seniors got, 6 weeks, something like that, 6 weeks left. Yeah, 5 weeks. I don't know. Not very long. Not very long. So that's coming up real quick. Let's take a look at 1, 2, 3. We'll see. 1, 2, 3, 4, 5. 6 weeks left, seniors. 6 weeks. That's it. So we got to get a lot wrapped up the next 6 weeks, and then we got a couple of people in the class that are not seniors, and both of those are not here right now. I love it. I've got 5 seniors in this class. You are here. We have 2 juniors. They're absent. Hopefully they'll be wandering in. They just ain't got their stuff together today. All right, we're going to take a look at our lessons, this matrices stuff. We're getting piled up with matrices. First hour, let's take a look. All right, so if we go to our grade screen and we scroll down, what is due on this? I only got 2 things here. I had 4. I've cut it back. Multiplying matrices and matrix quiz 2. But there's a lot to this. It's not just 2 lessons. There's a bunch of lessons. A lot of things we need to cover as we get into multiplying matrices because there's a lot of properties that are involved with this and stuff with the quiz. The quiz is going to cover stuff we covered last week as well. So let's go look at all of the lessons that we have to go with. So we're going up to matrix quiz 2. So basically everything up to that. And what did we do last week? Scalar multiplication. So let's go to activity screen. Let's see. Scalar multiplication was right there. And look, quiz 2 is here. We got 2 folders between us and quiz 2. So we need to look at the multiplying matrices folder, which has 2 lessons and the assignment. But under properties, which there's no assignments in this folder. Look, there is lots of things that need to be covered about multiplication of matrices, including identity and zero. This is stuff that's going to be on the quiz. These zero matrices, the identity matrices. So this is stuff we need to cover today so you'll understand it for the quiz. So let's get into this. We got a lot to go through. We're going to look at the intro to matrix multiplication. Some of this we may end up skipping in the interest of time, and you guys will cover it on your own before the quiz, but we'll see what we can get done here. Intro to matrix multiplication. Oh.
Let's say that we've got two matrices, and I'll just, for simplicity, I'll start with two 2 by 2 matrices. So let's say that this first one right over here is 2, -2, 5, and let's say 5 and 3. And then I have this matrix right over here that it's also going to be 2 by 2. And let's say it's -1, 4, let's say 7, and -6. And what I want to go through in this video, what I want to introduce you to is the convention, the mathematical convention for multiplying two matrices like this. And I want to stress that because mathematicians could have come up with a bunch of different ways to define matrix multiplication. But the convention that I'm going to show you is the way that it is done. And it's done this way, especially as you go into deeper linear algebra classes or you start doing computer graphics or even modeling different types of phenomena. You'll see why this type of matrix multiplication, which I'm about to show you, why it has the most applications. But I really want to stress, this is a human construct. Humans have found defining matrix multiplication the way I'm about to show you to be useful. So let's just think about how this could be. And once again, I want to stress it's a human construct. There's several ways that you could have thought about multiplying two 2 by 2 matrices. You could have done it the same way that you add matrices. When you add matrices, both matrices have to have the same dimensions, and you just add the corresponding entries in the matrices. So why don't we, one convention could have been, why don't we just, for a product right over here, why don't we just multiply corresponding entries? So 2 times -1 would put a -2 here. -2 times 4 put a -8 here. That's how we did addition. We added corresponding entries, but that is not the convention for multiplying matrices. That is not the standard convention. The standard convention for multiplying matrices is we're essentially going to take, to get this top left entry right over here, we're going to take the product of this row, of that row, with this column right over here. Now, what does it mean to take the product of a row and a column? And if you are familiar with vector dot products, this might ring a bell, where you take the product of the corresponding terms, the product of the first terms, products of the second terms, and then add those together. And so that's essentially what we're going to be doing. We're going to be taking the dot product of this first row and this first column to get this top left entry right over here. If the word dot product makes no sense to you, I will show you what that actually means. So, and actually let's get some more real estate here, just so I think it'll be useful, especially this very first time that we attempt to multiply matrices. So this top left entry, it's going to be 2 times -1. So 2 times -1 plus -2 times 7. Plus -2 times 7. So notice I took the product, first entry in the row, first entry in the column, those two products, then the product of second entry in the row, second entry in the column, that's right over there, and then I added them together. And that's essentially taking the dot product of this row vector and this column vector. If that doesn't make sense to you, if you're not familiar with vectors and dot products, don't worry about it. We just took the product of the first entry, product of the second entry, added them together to get, this is going to give us some number, and we'll calculate that in a few seconds. But let's think about the other ones. So to get this entry right over here, we're going to take the first row from this matrix and the second column from this matrix. And that kind of makes sense because we're still in the first row, but we're in the second column of the first row right here. First row, second column. So it's going to be 2 times 4 plus -2 times -6. And at this point, I encourage you to pause the video, seeing what you just saw, see if you can complete this. See if you can figure out the bottom left entry and the bottom right entry. And I'll give you a clue. It has something to do with this second row here. So I'm assuming you've given a go at it. Now let's just power through it together. Sometimes matrix multiplication can get a little bit intense. So we're now in the second row. So we're going to use the second row of this first matrix. And for this entry, second row, first column. Second row, first column. 5 times -1. 5 times -1 plus 3 times 7. Plus 3 times 7. And then finally, we're in the home stretch now. To get to get this bottom row second column, or second row second column, we multiply this row essentially by this column right over here. So it is going to be 5 times 4, 5 times 4, plus 3 times negative 6, plus 3 times negative 6. Now what does all of this simplify to? So this is going to be equal to, let's see, so negative 2 plus negative 14, that's going to be negative 16. That right over there is negative 16. Then we have 8 plus 12, so that's going to be 20. And then we have negative 5 plus 21, which is going to be 16, positive 16. Did I do that right? Yep, positive 16. And then finally, you're going to have 20 minus 18. So that's just going to be 2. So the product of these two matrices, we deserve a little bit of a drum roll at this point. When we multiply this 2 by 2 matrix times this 2 by 2 matrix, we are going to get negative 16, 20, 20, 16, and 16, and 2. And we are done.
Hope you were paying attention there. Multiplying matrices is quite different than scalar multiplication or adding or subtracting matrices, because you're taking an entire row, an entire column, and multiplying each of the elements and then add them together to get one number on that. So that's a little bit different than what we've seen before. Let me do a sample on paper just to show you exactly what we're doing there, as another example before we look at more of Sal's videos there. So I'm going to take, hopefully a sharpened pencil, and we're going to do another 2 by 2 just to reinforce what he told us about multiplying matrices together. And let's just do this as a 1, 2, 3, 4, and a 5, 6, 7, 8, just to make it simple. Oh, boy, that is bleaching us out today. There we go. That's a little better. Okay, so multiplying these, remember we take this first row and the first column, and this is going to give us our first number, because our first answer will be the first row, first column answer. So first row, first column. I'm going to raise this up a little bit, see if it quits bleaching us out so bad. So to get the answer that goes in the first row in the first column, we're going to take the first row times the first column. So we're going to take the first elements, right? The first thing in the row and the first thing in the column, the 1 and the 5. And we're going to take 1 times 5. And then we're going to add that together, 1 times 5, to 2 times 7. First numbers, second numbers. First numbers, second numbers. 1 times 5 is 5. 2 times 7 is 14. So 19 is the product. When we add the two products together, that is what our answer is for the first row times the first column. Now, to get the first row second column answer, we take the first row times the second column. So we take 1 times 6 and add that to 2 times 8. So 6, 1 times 6 is 6, 2 times 8 is 16. So this is 22. Okay, now we're moving down to the second row. So we're going to use the second row's numbers. Since we're doing second row, we're going to do second row number. So we're going to start out with the second row times the first column, because this is the first column. So anytime you got answers for the second row, you have to use the second row in the first matrix. 3 times 5. And then 4 times 7. 3 times 5 is 15. 4 times 7 is 28. And we add those together, and we got 43. Now this last one, As you would expect, we take the second row here and the second column to get the second row, second column answer. 3 times 6 plus 4 times 8. 18, 32. So when you multiply this matrix times this matrix, you get this 19, 22, 43, and 50. You say this is very, very different than addition and subtraction or scalar multiplication. So you really got to practice this. You really got to pay attention to make sure you understand which row, which column that you're doing this with so you can keep that straight. This was just a 2 by 2 matrix. It gets a little bit more complicated when we do bigger matrices. Now, here's the other thing. With addition and subtraction, we could only add or subtract matrices if they were the exact same size. That's not true with multiplication. And we're going to see that in this next example that he gives us here. So let me get the next lesson up here and I'll present this. So pay attention how it works. It's not hard to figure out if you can multiply two matrices together if you're paying attention. So really, you may want to make notes of this, but you definitely want to pay attention. Multiplying a matrix by a matrix. And this one's not going to be a 2 by 2. This is showing bigger ones.
We're given two matrices over here, matrix E and matrix D, and they ask us what is ED, which is another way of saying what is the product of matrix E and matrix D. So just so I remember what I'm doing, let me copy and paste this, and then I'm going to get out my little scratch pad. So let me paste that over here. So we have all the information we needed. And so let's try to work this out. So matrix E times matrix D. So this is matrix E times matrix D, which is equal to, matrix E is all of this business. So it is 0, 3, 5, 5, 5, 2 times matrix D, which is all of this. So we're going to multiply it times 3, 3, 4, 4, negative 2, negative 2. Now, the first thing that we have to check is whether this is even a valid operation. Now, the matrix multiplication is a human-defined operation that just happens, in fact, all operations are, that happen to have neat properties. Now, the way that us humans have defined matrix multiplication, it only works if when we're multiplying our two matrices, so this right over here has 2 rows and 3 columns, so it's a 2 by 3 matrix, and this has 3 rows and 2 columns, it's 3 by 2. This only works, we can only multiply this matrix times this matrix if the number of columns on this matrix is equal to the number of rows on this matrix. And in this situation it is, so I can actually multiply them. If these two numbers weren't equal, if the number of columns here were not equal to the number of rows here, then this would not be a valid operation, at least the way that we have defined matrix multiplication. The other thing you always have to remember is that E times...
Okay, I'm going to pause that for just a second because this is important. You can only multiply two matrices together if those middle numbers are the same. You write your two matrices down that you're trying to multiply, put the size underneath them. This is a 2 by 3. This is a 3 by 2. Check those middle numbers. If those middle numbers are not the same, then you cannot multiply them together. He said that, but I want to emphasize this. The columns here has to match the rows here. Those middle numbers have to be the same. Now, here's something else that's cool that this also tells you. If these are the same, then the answer is going to be the other two numbers. When you multiply this 2 by 3 by 3 by 2, the answer is going to be a 2 by 2. 2 by 2. So we're multiplying together a 2 by 3 and a 3 by 2, and the answer is going to be a 2 by 2. But you really need to write these dimensions underneath the two matrices to know if you can even multiply it. If this was a 2 by 2 and a 3 by 2, they wouldn't match. Has to be the same numbers. You back it up just a little bit and continue.
operation, at least the way that we have defined matrix multiplication. The other thing you always have to remember is that E times D is not always the same thing as D times E. Order matters when you're multiplying matrices. It doesn't matter if you're multiplying regular numbers, but it matters for matrices. But let's actually work this out. So what we're going to get is actually going to be a 2 by 2 matrix, but I'm going to create some space here because we're going to have to do some computation. So this is going to be equal to, I'm going to make a huge 2 by 2 matrix here. So the way we get the top left entry is essentially going to be, it's going to be this row times this product. If you view them each as vectors and you have some familiar with the dot product, we're essentially going to take the dot product of that and that. And if you have no idea what that is, I'm about to show you. This entry is going to be 0 times 3. So 0 times 3 plus 3 times 3 plus 3 times 3 plus 5 times 4 plus 5 times 4. So that is the top left entry. And I already see that I'm going to run out of space here. So let me move this over. To the right, some space, so I have some breathing room. Now we can do the top right entry. This was the top left. Now we're going to do the top right. So the top right entry is going to be this row times this column. Notice the entry is getting the row from the first matrix and the column from the second one. That's kind of determining its position. So once again, this is going to be 0 times 4 plus 3 times negative 2, 3 times negative 2, plus 5 times negative 2, 5 times negative 2. And we keep going. The bottom left entry is going to be this row, the second row here, times the first column here. So it's 5 times 3. So 5 times 3 plus 5 times 3 plus 5 times 3 plus 2 times 4 plus 2 times 4. And we're almost done. We just need to multiply or take the dot product of this row with this column right over here. So it's going to be 5 times 4 plus 5 times negative 2 plus 2 times negative 2. 2 times negative 2. And so this is going to be equal to, and we can just evaluate this now. Let's see. 0 times 3 is 0. This is 9 plus 20. This is 29. This all simplified to 29. All of this is 0. This is negative 6. And then this is minus 10. So this all simplifies to negative 16. Negative 16. This right over here, it's 15 plus 15, which is 30, plus 8. So this is 38. 38. And then finally, this is 20 minus 10 minus 4. So this is going to be 6. So this is all going to simplify to 6. So this all became 29, negative 16, 38, and 6. 29, negative 16, 38, and 6. So 29, negative 16, 38, and 6. Let's check our answer. We got it right.
All right. As we said, he ended up with a 2 by 2. It was a 2 by 3 multiplied by 3 times 2. You end up with a 2 by 2, the outside numbers. The middle numbers tell you if you can multiply it. The outside numbers tell you what size the answer is going to be. So again, multiplying matrices, got to pay a little bit of attention. Let's go ahead and look at the assignment that goes with that, because that's our first assignment this week, is the multiplying matrices assignment. So we're going to look at one of those together, and I'll leave that for you. But remember, you're going to scroll down and paste your score down here. After it logs you in, make sure you're logged in, got your name up the top. Okay, ready to practice. Here's the 4 questions. First one has us do, let H be E times B, EB. Find H. So it wants us to multiply a 2 by 2 times a 2 by 3. 2 by 2 times 2 times 3. The middle numbers are both 2s. So we should have a 2 by 3 answer. So let's write this. We're going to do this one together. We're going to write this one down. Let's switch over here to this. All right. We got -1, 3, 0, 4, -5, 0, 5, -2, 5, 2, 2. I'm going to give myself a lot of room under here. So I need this first row times the first column. -1 times 0 plus 3 times 5. So if I want to do this as we go, -1 times 0 is 0. 3 times 5 is 15. So the first entry for our answer is 15. Now the middle one, because there's going to be 3 columns here. -1 times 3 times this column. -1 times 5 plus 3 times 2. So this is -5. This is 6. We're adding them together. So it's just 1. Focus. There we go. Now the first row times the third one. -1 times -2. -1 times -2 added to 3 times 2. -1 times -2 is 2. 3 times 2 is 6. So 8. All right, now we're going to do the exact same thing, just using the second row. 0 and 4. 0. So 0 times 0 plus 4 times 5. 0, 4 times 5 is 20. Okay, now we've got 0 times 5, because going to the second column now, and 4 times 2. 4 times 2. 0 times 5 is 0. 4 times 2 is 8. Now the last column. 0 times -2 plus 4 times 2. Well, again, that's 0. 4 times 2 is 8. So if we multiply E times B, which, again, when you checked it, this is a 2 by 2, right? 2 rows, 2 columns, multiplied times a 2 rows by 3 columns. Since the middle 2 numbers are the same, those are both 2s, we do know that this will multiply, and the answer will be a 2 by 3. And it is, look, 2, 3. But this is the answer we need to put in, and let's see if we're right here. So it's a 15, 1, and an 8, and a 28 and 8. Great work. So we did the first one together there. Now, again, you'll have different ones because it randomizes for everybody. But you go through the exact same process I just did. Now it's got a 2 by 2 multiplied by a 2 by 2. So you know those will multiply because the middle numbers are 2s, and you're going to end up with a 2 by 2 as an answer. All right, I'm not going to continue through all of those, but yeah, when you get your score, take a screenshot, paste it in there. And that is the first assignment for this week, multiply matrices. Now, the other assignment is this quiz, but here are several things we need to look at before we get to this quiz. Let's see if we have time for all of them. Define matrix operations video lesson. All right, so let's look at what matrix operations we're defining.
So we have matrix D and matrix B, and they ask us, is DB defined? Is the product D times B defined? So D times B is going to be defined is if, let me make this very clear, and this is how I think about it. So let me copy and paste it so I can do this on my scratch pad. So to answer that question, get out a scratch pad right over here. Let me paste the question right here. So let's think about these two matrices. Let's think about these two matrices. You first have matrix D, You first have matrix D. I'll do a nice bold D here. And it has 3 rows and 3 columns. So it is a 3 by 3 matrix. And then you want to multiply that times matrix B. Matrix B is a 2 by 2 matrix. The only way that we know to define matrix multiplication is if these middle two numbers are the same. If the number of columns D has is equal to the number of rows B has. Now in this case, they clearly do not equal each other, so matrix multiplication is not defined here. So let's go back there and say no. No, DB is not defined. Let's do a few more of these examples. So we have a 2 by 1. You could view this as a 2 by 1 matrix, or you could view this as a column vector. This is another 2 by 1 matrix or a column vector. C plus B defined. Well, matrix addition is defined if both matrices have the exact same dimensions. And these two matrices do have the exact same dimensions. And the reason why is because with matrix addition, you just add every corresponding term. So in the sum, the top, it'll actually be 4 plus 0 over negative 2 plus 0, which is still just going to be the same thing as this matrix up here. But what they're asking, is this defined? Absolutely. These both are 2 by 1 matrices. So yes, it is defined. Let's do one more. So once again, they're asking us, is the product A times E defined? So here you have a 2 by 2 matrix. Let me copy and paste this just so we can make sure that we know what we're talking about. So get my scratch pad out. So this top matrix right over here. So matrix A is a 2 by 2 matrix, and matrix E, so we're going to multiply it times matrix E, which has 1 row and 2 columns. 1 row and 2 columns. So in this scenario, once again, the number of columns matrix A has is 2, and the number of rows matrix E has is 1. So this will not be defined. These two things have to be the same for them to be defined. Now, what is interesting is if you did it the other way around, if you took E times A, let's check if this would have been defined. Matrix E is 1 by 2, 1 row times 2 columns. Matrix A is 2 rows times 2, or 2 by 2, 2 rows and 2 columns. And so this would have been defined. Matrix E has 2 columns, which is exactly the same number of rows that matrix A has. And this really hits the point home that the order matters when you multiply matrices. But for the sake of this question, is AE defined? No, it isn't. And so we can check our answer. No, it isn't.
So yeah, I think that's something that's very interesting. If we go back and look at, let me pause that. You made a really good point down here. With A and E, you cannot multiply A times E, but you can multiply E times A. See, this is very different. Matrix multiplication is very different than just the rules we're used to. You know, in normal mathematical operations, 2 times 5 is the same as 5 times 2. It doesn't matter which way we do that. With a matrix, it does matter because we cannot multiply A times E because the dimensions are not right. But we can multiply E times A. So very, very different. You have to pay attention with matrices on when you can multiply. This one you can't. And the answer for this is a 1 by 2 when you multiply E times A. So makes a difference. You have to pay attention. You have to pay attention when you get to a matrices. All right. We're going to, let's see, multiply matrix dimensions. I think we've talked about that enough. Let's go to the identity matrices lessons. Let me put this up on the screen. All right. What you should be familiar with. You should know that's a 2 by 3, basically. All right. And that talks about the multiplication, how to multiply them. So let's talk about identity matrix. An n by n, whatever size, n can be whatever, identity matrix is, and you can just put in because it's always, notice it's the same size. If n is 2, it's a 2 by 2. If n is 4, it's a 4 by 4. If n is 1, it's a 1 by 1. You know, so n is the same number. So you can just put I3 to mean a 3 by 3. And here is the thing about an identity matrix. Identity matrix. Got to recognize that term. Notice what a identity matrix 2 by 2 looks like. It's a 1 0 0 1. A 3 is a 1 0 0 0 1 0 0 0 1. Notice basically that middle diagonal column, row, column, diagonal is all ones. Everything else is zeros. And we use the identity matrix to multiply against other matrices. So when you multiply by the identity matrix, this is going to be interesting. We're going to do this on paper to see what it means when we multiply by an identity matrix, because identity matrix means something. It's a special kind of matrix. 1 0 0 1 times 2 3 5 1. This is an identity matrix. 1 0 0 1. When we multiply these, we'll multiply this out. They're both, it's a 2 by 2 being multiplied by a 2 by 2. So those middle numbers are the same. We can multiply, and we're going to end up with a 2 by 2. So this is going to be a 2 by 2 answer. Now let's do the math. Remember, we start out with the first row multiplied by the first column. 1 times 2 plus 0 times 5. 1 times 2 is 2. 0 times 5 is 0. So this is just a 2. Now let's do the first row times the second column. 1 times 3. 1 times 3 plus 0 times 1. That's just 0. 1 times 3 is 3. Now we're down in the second row, so we need to use the second row right here. 0 times 2. 1 times 5. 0 times 2 is 0 plus 1 times 5 is 5. And then finally 0 times 3, and then 1 times 1. That's 0, that's 1. Well, looky there. We multiplied this matrix times the identity matrix, and look what we ended up with. So if this was an identity matrix, this was A, what did we end up with? A. So the identity matrix times A equals A. So an identity matrix is the same as multiplying times 1. That's really what we did. We multiplied this matrix times 1 because we got itself. 1 times A equals A. Identity matrix is a matrix that multiplies by 1. So that's handy to know. There's going to be some questions in our quiz this week to where you have to understand what an identity matrix will do. An identity matrix won't change anything. It basically just says whatever this matrix is, it's still going to be after we multiply it by an identity matrix. Interesting. So if we know this is an identity matrix, then we know it's going to be 2, 3, 5, and 1. Check. Correct. Look, this is an identity matrix, I3, multiplied by that. So we don't even have to do the math. If it's an identity matrix, it's going to end up exactly what it started as. Look at that. I just copied A because the identity matrix times A is going to equal A. Oh, see, that's a nice shortcut. If you understand an identity matrix and can recognize it, It'll save you some time. So basically, A times identity matrix, it's the same as identity matrix times A. You can do those in either order. It's going to end up exactly the same, but it equals the original. So it's just like multiplying something times 1. A times 1 or 1 times A, you will get A's. Two real numbers whose product is the multiplicative identity. Oh, this is interesting. So 1/3 and 3. You may not have used these terms much in math, but those are multiplicative inverses. Multiplicative inverses, 1/3 and 3. Because when you multiply them together, you just get 1. So any two numbers that you multiply together, you would just get 1. So you can have matrices that are multiplicative inverses. So you can multiply this A times this B and get the identity matrix, as I'd like to see this. If we click on this, it'll show us the math. If you multiply 2 times -4 plus 3 times 3, it all comes down to where it ends up 1, 0, 0, 1. It ends up the identity matrix. So you can have two matrices that multiply together to get you the identity matrix. They're called multiplicative inverses. And let's see. And that's AB. Let's see if BA works the same way. And BA works the same way. In this case, they're both 2 by 2s. So they can be multiplied in either order. And they end up with multiplicative inverses. So the main thing is just to understand what an identity matrix does. It doesn't change anything because it's like multiplying by 1. All right, so that was, I'm going to close this folder for now. That was the identity matrix. Now, here's a lesson that went with the video we saw. If you want to go back and do some of those practice problems, they're there. Dimensions of an identity matrix. We'll go ahead and take a look at that real quick. The dimensions of an identity matrix.
Let's say that you've got some matrix C. I'm trying my best to bold it to make sure you realize that this is a matrix. And let's say that we know that it has A rows and B columns. So it's an A by B matrix. And let's say that we are going to multiply it by some identity matrix. Some identity matrix. Once again, let me do my best attempt to bold this right over here. So we're going to multiply the identity matrix I times C. And of course, we are going to get C again because that's the identity matrix. That's the property of the identity matrix. And of course, C, we already know, is an A by B matrix. A rows and B columns. And B columns. Now, based on this, what are the dimensions of I going to be? And I encourage you to pause this video and think about it on your own.
Hey, we are going to pause that because in order to multiply two matrices together, remember what has to be true. Those middle numbers, which would be the columns of the first matrix, and the rows of the second matrix have to be the same. So this is going to be something times A. It's got to be the same as that because if it's not A, it can't even be multiplied. And the answer is going to be an A times B. Well, that's the outside numbers. So this also has to be an A. So this has to be an A times A matrix in order to be even multiplied by A times B and end up with an A times B. He's going to explain that, but that's important to understand. How big does the identity matrix have to be? What size would it need to be able to multiply it times this A times B C matrix?
So we've already done this exercise a little bit where we first looked at identity matrices, but now we're doing it with we're multiplying the identity matrix times a very general matrix. I'm just even speaking in generalities about its dimensions. Well, one thing we know is that matrix multiplication is only defined is if the number of columns of the first matrix is equal to the number of rows of the second matrix. So this one has A rows, so this one's going to have A columns. It's going to have A columns. So it's going to have A columns. Now, how many rows is this one going to have? Well, we already know that matrix multiplication is only defined if the number of columns on the first matrix is equal to the number of rows on the second one. And we know that the product gets its number of rows. We know the product gets its number of rows from the number of rows of the first matrix being multiplied. So if the product has A rows, then the identity matrix right over here has to have A rows. Now, what's interesting about this? When we first got introduced to identity matrices, we were multiplying, we picked out a 3 by 3 example, and we got a 3 by 3 identity matrix. What's interesting about what we've just proven to ourselves is the identity matrix for any matrix, even a non-square matrix. A and B could be two different values. The identity matrix for any matrix is going to be a square matrix. It's going to have the same number of rows and the same number of columns. And so when we think about identity matrices, we can really just say, well, is this the identity matrix that is a 4 by 4? Is it a 3 by 3? Is it a 2 by 2? Or I guess even a 1 by 1? And so the convention isn't even to write identity 2 by 2 is equal to 1, 0, 0, 1. The convention is actually to just write I2 because it's going to be a 2 by 2. It's going to be a 2 by 2 matrix, so it's going to be 1, 0, 0, 1. Identity 5 is going to be a 5 by 5 matrix, so it's going to be 1, 1, 2, 3, 4, 0, 1, 2, 1, 2, 3, 0, 0, 1, 1, 0, 0, 0. You get the idea. 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. Just like that. The whole point here is just to realize that your identity matrix is always going to be a square matrix. And it works even when you're multiplying non-square other matrices.
Okay, so that was the identity matrix. So now let's look to see, is matrix multiplication commutative?
We know that the multiplication of scalar quantities is commutative. For example, 5 times 7 is the same thing as 7 times 5. And that's obviously just a particular example. I could give many, many more. 3 times negative 11 is the same thing as negative 11 times 3. And the whole point of commutativity, I can never say it, is that it doesn't matter what order that I'm multiplying in. This is the same thing as negative 11 times 3. Or if we wanted to speak in general terms, if I have the scalar a and I multiply it times the scalar b, that's going to be the same thing as multiplying the scalar b times the scalar a. Now what I want to do in this video is think about whether this property of commutativity, whether the commutative property of multiplication of scalars, whether there's a similar property for the multiplication of matrices. Whether it's the case that if I had two matrices, let's say matrix capital A and matrix capital B, whether it's always the case that that product, the resulting matrix here, is the same as the product of matrix B and matrix A, just swapping the order. And I encourage you, so is this always true? It might be sometimes true, but in order for us to say that matrix multiplication is commutative, that it doesn't matter what order we are multiplying it, we have to figure out, is this always going to be true? And I encourage you to pause this video and think about that for a little bit. Well, let's just think through a few things. First of all, let's just think about matrices of different dimensions. So let's say I have a matrix here. Let's say that matrix A is a, I don't know, let's say it is a 5 by 2 matrix. 5 by 2 matrix. And matrix B is a 2 by 3 matrix. So the product AB is going to have what dimensions? So if I multiply these two, you're going to get a third matrix. Let's just call that C for now. You're going to get a third matrix C. And what are going to be the dimensions of C? Well, we know that first of all, that this product is defined under our convention of matrix multiplication because the number of columns that A has is the same as the number of rows B has, and the resulting rows and column are going to be the rows of A and the columns of B. So C is going to be a 5 by 3 matrix. A 5 by 3 matrix. Now, what about the other way around? What would b times a be? And once again, I encourage you to pause the video. So if you were to take b, so let me copy and paste that, and multiply that times a. So I'm really just switching the order of the multiplication. So copy and paste. So if we take that product right over there, what is that going to be equal to? What is this? What is this right over here going to be equal to? Well, the first question is matrix multiplication even defined for these two matrices? And when you look at the number of columns that B has and the number of rows that A has, you see that it actually is not defined, that we have a different number of columns for B and a different number of rows for A. So here, the product is not defined. Is not defined. So this immediately is a pretty big clue that this isn't always going to be true. Here, AB, the product AB is defined, and you'll end up with a 5 by 3 matrix. The product here, BA, isn't even defined. So this is already, we're already seeing that this is not the case, that order matters when you are multiplying matrices. And to make things a little bit more concrete, let's actually look at a matrix. You might be saying, oh, maybe this doesn't work only when it's not defined, but hey, maybe it works if we're always dealing with square matrices or matrices where both products are always defined in some way, or maybe or some other case. And so let's look at a case where we're dealing with two by two matrices and see whether order matters. So let's say I have the matrix. Let's say I have the matrix 1, 2, -3, -4, and I want to multiply that by the matrix -2, 0, 0, -3. What's that product going to be? And once again, I encourage you to pause the video and think about that. Well, let's think it through, and we've done this many times now. So this first entry here is going to be, we're essentially going to look at this row and this column. So it's 1 times -2, which is -2, plus 2 times 0. So this is going to be -2. And now for this entry over here, we'll look at this row and this column. So 1 times 0, which is 0, plus 2 times -3, which is -6. And then for this entry, we would look at this row and this column. So -3 times -2 is +6 plus -4 times 0, which is just +6. So you're going to have +6. And then finally, for this entry, it's going to be the second row times the second column. -3 times 0 is 0. -4 times -3 is +12. So fair enough. Now what if we did it the other way around? What if we were to multiply? -2, 0, 0, -3 times 1, 2, -3, -4.
Okay, so this is good to pay attention to. So in this case, it's a 2 by 2 times a 2 by 2. So it doesn't matter if we multiply A times B or B times A, it is valid either way because all the numbers are 2s. The middle numbers are 2s, the outside numbers are 2s. So this will answer a good question. If it's defined, if you can actually do the multiplication, does it work the same? A times B, B times A, is that the exact same thing? 2 times 4 is 4 times 2, it's 8 either way. Let's see if it works with matrices. So pay attention here. That was our answer when we multiplied A times B. Now let's see what it is when we take B times A.
What's this going to be equal to? And as always, it's a good idea to try to pause it and work through it on your own. So let's think about this. So -2 times 1 is -2 plus 0 times -3. So that's going to be -2. So far it's looking pretty good. Then if you have -2 times 2 is -4, plus 0 times -4 is -4. So we already see that these two things aren't going to be equal. But let's just finish it just so that we have a feeling of completion. So this entry right here is going to be the second row, first column. 0 times 1 plus -3 times -3 is +9. Once again, doesn't match up. And then finally, 0 times 2 is 0 plus -3 times -4 is is positive 12. So that one actually did match up. But clearly, these two products are not the same thing. The order with which, even though it's defined, it doesn't matter whether you take the yellow one times the purple one or the purple one times the yellow one, both of those result in a defined product, but we see it's not the same product. So once again, another case showing that, that multiplication of matrices is not commutative.
Not commutative. It is not the same. A times B is not the same as B times A. All right, here's the other thing we're going to look at. We looked at matrix multiplication, how that works, when you can do it, when you can't. We've looked at an identity matrix, which means multiplying by 1. Now we're going to look more at a zero matrix. We've got 2 videos left for this week. And we're going to look at zero matrices. So let's check this out.
Drawing analogies between, I guess we could say, traditional multiplication or scalar multiplication. And the first one we drew is when you have traditional multiplication, you multiply 1 times any number, and you get that number again. And you could view 1 as essentially the identity number, or this is the identity property of multiplication. You multiply 1 times any number, you get that number again. And that essentially inspired our thinking behind having identity matrices. That, hey, maybe there are some matrices that if I multiply it times some other matrix, I am going to get that matrix again. And you've probably shown for yourselves that you can do it in either way. You could have some matrix times an identity matrix and get that matrix again. Now, if matrix A right over here is a square matrix, then in either situation, this identity matrix is going to be the same identity matrix. But if matrix A is not a square matrix, then these are going to be 2 different identity matrices depending on the appropriate dimensions. Now, let's see if we can extend this analogy between traditional multiplication and matrix multiplication. We know that there's another special number in traditional multiplication, and that's a 0. So we know that 0 times anything is equal to 0, or anything times 0 is equal to 0. So what would be the analogy if we're thinking about matrix multiplication? Well, it would be some matrix that if I were to multiply it times another matrix, I get, I guess you could say, that same 0 matrix again. And that is what we call it. We call it a 0 matrix. So if I take some matrix A, and essentially if I multiply it times one of these 0 matrices, or if I multiply one of these 0 matrices times A, I should get another 0 matrix. And it depends on the dimensions. You might not get a 0 matrix with the same dimensions. It depends what the dimensions of A are going to be, but you could imagine what a 0 matrix might look like. For example, if A is 1, 2, 3, 4, what's a 0 matrix that I can multiply this by to get another 0 matrix? Well, it might be pretty straightforward. If you just had a ton of zeros here, when you multiply this out, you're going to get this. You take the dot product of this row and this column, 0 times 1 plus 0 times 3 is going to be 0. You keep going, 0, 0, 0, 0. If we had a, and just to make the point clear, let's say we had a matrix 1, 2, 3, 4, 5, 6, 5, 6. So over here, we want to multiply this times, let's see, in order for the matrix multiplication to work, my 0 matrix has got to have the same number of columns as this one has rows. So it's got to have 2 columns, but I could make it have 3 rows. So it could look like this, 0, 0, 0, 0, 0. And I encourage you to multiply these two. Pause the video right now and see what you get. Well, when you multiply them, let's think about it. So the top left entry, so this is, let me just write the dimensions. This is a 3 by 2 matrix. This is a 2 by 3 matrix. So we know that we have valid matrix multiplication going on right over here. Same number, the number of columns in the first matrix is equal to the number of rows in the second one. And we also know that the resulting product is going to be a 3 by 3 matrix. So it's going to be a 3 by 3 matrix. And I'll leave it up to you to verify that all the entries here are going to be, all of the entries here are going to be 0. And it makes sense. You could go through the math, but you could see, well, you just, every time you're multiplying, say, this row by this column to get that entry, well, you just have 0 times 1 plus 0 times 4 to get that 0 there. But the whole point of showing you this example is we have one 0 matrix multiplying by this, being multiplied by this matrix right over here, and then we get another 0 matrix, but it has different dimensions.
All right, so we saw a few differences there. With a 0 matrix, you always end up with 0 when you multiply a matrix. So it's a matrix full of zeros. But as we saw in this example, 0 matrices do not have to be square. Like the identity matrices are always 2 by 2s, 3 by 3s, 4 by 4s. But he had a 0 matrix that was a 3 by 2. So a 0 matrix does not have to be square, 2 by 2, 3 by 3, or anything like that. It would just be filled with zeros. Filled with zeros. All right, let's look at our last lesson. And this one's really good because there is a problem in our quiz that is exactly like what he's going to do in this video. So this will help you be able to nail it in the quiz. You pay attention to what he's doing in this video right here.
So we have a matrix equation set up right over here. We have matrix A times this plus matrix B times this plus matrix C times this is equal to this 2 by 2 matrix. And the way it's set up, it's a little bit of a puzzle. And I'll give you one clue as to what type of matrices A, B, and C could be. They're each either going to be an identity matrix, or a 0 matrix. So given that clue that each of these are either an identity matrix or a 0 matrix, can you pause this video and essentially solve this puzzle? Which of these are identity matrices and which of these are 0 matrices?
All right, so just so you understand what he's talking about there, we have 6 matrices being multiplied or being in this problem. A times this matrix, right? So there's 2 matrices right here. A is either an identity matrix or a 0 matrix. We don't know which. It's one or the other. And B is either an identity matrix or 0 matrix, and C is. So we had A plus this matrix plus B plus this matrix plus C plus this matrix. So we have 6 matrices we're using, and the answer is right here with the 2, 4, 7, 0. So the question is, and like I said, there's a question in our quiz, A, B, and C. We have to figure out which of those would be identity matrices and which of those would be a 0 matrix. Well, what do we know about identity and 0 matrix? If, let's say, for example, if A was a 0 matrix, that means that A times this matrix would be 0. So we would just totally ignore that and we would just add these two together. If we said B and C are both identity, that means they're being multiplied by 1. So I mean 1 plus 1 is 2, negative 5 plus 1 is 4, 1 plus 3 is 7, 3 plus 2 is 0. Well, that didn't work. So B and C must not both be identity and A being 0, because if we add these 2 matrices together, we don't get that answer. So what you're looking at is, which of these do I need to add together? Because these are being added. Which of these add together to equal this? That will tell me which of A, B, and C are 0 matrices and which of them are identity matrices. So if we look at this, let's look at the 7. We've got a 4, we have a 1, we have a 3. When we add 2 of those together, we get 7. If we add this first one and this one, the 4 plus 3 is 7. Negative 2 plus 2 is 0. 1 plus 1 is 2. 3 plus 1 is 4. So if we add this 1 here at the beginning to the 1 in front of after the C, we can get this answer. So that means B must be a 0 matrix, because this must all be 0. Because if we add 1 plus 0 plus 1, we'll get 2. We get 3 plus 0 plus 1, we get 4. 4 plus 0 plus 3. So A and C have to be identity matrices, and B has to be a 0 matrix just to make that math work. Let's let him go through that there.
I'm assuming you've given a go at it. So let's go entry by entry. So if you look at this first entry right over here, how can we get a 2 for this top left entry? Well, let's see. When we multiply, if any of these are identities, then essentially you just get the value of the matrix. If any of these are 0, then essentially that product doesn't get added. It's one way of thinking about it, is that matrix won't matter anymore because it's going to be multiplied by 0. So if A was a 0 matrix and B and C were identity matrices, you would add 1 plus 1 to get 2. So you're like, oh, maybe that's the case. But it could be the other way around. It could be that A is identity matrix, B is a 0 matrix, and C is an identity matrix, and you add 1 plus 1 over there to get 2. Or you could say that maybe C is the 0 matrix and B is the identity matrix, and you add 1 plus 1 here. So really all this is telling us is two of A, B, and C are going to be identity matrices, and one is going to be a 0 matrix, but we don't know which one is which just yet. Any of them can be the 0 matrix, at least based on looking at that first entry. Now let's look at, let's look at this entry right over here. How can we add up to 4? Well, let's see. 3, if this was an identity matrix and this was an identity matrix, then then essentially you'll just be left with this matrix plus this matrix, and this is going to be the 0. So 3 plus -5, that is not equal to 4. So both of you can't have A and B be identity matrices and C be the 0 matrix. So let's think about other combinations here. So what about B and C being the identity matrices and A being the 0 matrix? In that situation, so A is the 0 matrix, so that's not going to matter. And we're essentially, when you multiply B times this, you're just going to get this matrix, and C times this, you're going to get that matrix, if B and C are identity matrices. And so you have -5 plus 1 would be -4. So that doesn't work either. So our last scenario is going to be, so we can essentially rule out B as an identity matrix, because when we had B be one of the identity matrices and we picked the other two options, we still couldn't get to 4 here. So B is going to be a 0 matrix, and let's see if that works out. A is identity, then A would be an identity, and C would be an identity matrix as well. So let's see if that actually makes sense. So if this right over here is identity matrix and that over there is an identity matrix, this whole thing simplifies to 1, 3, 4, comma, -2 plus 1, 1, 3, 2. And it does indeed equal 1 plus 1 is 2, 3 plus 1 is 4, 4 plus 3 is 7, -2 plus 2 is indeed 0.
It's a nice walkthrough on that. That covers all of the videos and lessons that we need to cover under the properties. Let's look at the quiz, and then I'll let you guys go because that's all we have left. Oh, look, you have 2 attempts. So if you don't do well the first time, go back and look at it again. All right, here it is. This first one, they want you to multiply C times D. There's C, it's a 3 by 4, and this is a 4 by 2. Put an X over any cell that you don't need, because they gave you a 4 by 4 as the answer. You don't need a 4 by 4 because this is a 3 by 4 and a 4 by 2. Put an X on it. Here's the ones which are defined: A times B, A times B, B times A. But it gives you the dimensions: 9 by 4 and a 3 by 9. Can we multiply A times B if A is a 9 by 4 and B is a 3 times 9? Or the other way around. A, B, and C are 4 by 4 matrices. 0 is a 0 matrix, which is false. There's 4 cases. Only one of them is false. It does not say select all correct answers. Only one of these must be false. This one says select all correct answers. This is the video he just did. A, B, and C are either identity or 0 matrices. A times this matrix plus B times this matrix minus, pay attention, this one has a minus. His video was all pluses. Minus C times this matrix. Can you just add these two together and this is a 0? Or just one of these need to be a 0? And you subtract this one to get this answer. There you go. Select all correct answers. Which ones must be identity? It may ask you which one's a 0. So just pay attention to that. But that's it. 4 questions, and you do get 2 attempts. 2 attempts. So get some pencil and paper out when you have to multiply those matrices, because you saw how much work that is. You don't want to try to do all that in your head, especially since that's like a 3x4, or this isn't 2x2s. 2x2s are a lot easier to do in your head. When you got a lot of numbers, you want to have some pencil and paper to do that. So, all right, guys, that's it for the week. Lots of information there. Lots of information, because matrices, when you're dealing with multiplication, is a lot trickier than just adding and subtracting, right? But you can do this. It's not like you're dealing with crazy numbers. You're multiplying 3 times -4, stuff like that. You just have to pay attention to which rows and which columns you're using. So, okay, well, welcome to April. Have a great week. I'll let you go. That's everything we got. If you have questions, this is a B-Day Friday, so I'll be in class on Wednesday this week, Wednesday only. So if you have below 70%, I'll see you Wednesday. If you have questions, I'll see you Wednesday. Otherwise, have a great week, guys. Have a good one.